Hello everyone. The title of this video is Graphing an Absolute Value Function. So every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org, and I'm in their Algebra and Trigonometry text, section 3.6, called Absolute Value Functions, and I'm under the heading Graphing an Absolute Value Function. Alright, so each example I'm going to do is either going to be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Okay, so I've got written out here, again we're under the Graphing an Absolute Value Function heading. The first example I want to show you is example 2 from the reading, from the text. So let's take a look at that. Right, so you got some stuff to read here. Example 2 is right here, right? And it's writing an equation for an absolute value function given a graph. So write an equation for the function graphed in this figure. Now this is kind of this is very closely related to what I've done in the previous couple videos on function transformations. So what we see here is one of those absolute value of a linear function, right? One of those V-shaped graphs. So what I'm going to be doing is taking the toolkit function, the basic library function, the absolute value function from the basic library, taking that basic absolute value function and performing transformations to change it into this function they're giving us here. Okay, so let me go to my paper, and hopefully you recall. So I'm going to start with one of our toolkit functions, which is the absolute value function, y equals the just the absolute value of x, which you should know what that looks like. I'm going to make a rough sketch of it over here. That has 0, 0, and the absolute value of 1 is 1, absolute value of -1 is 1, and it's just this V-shaped graph, right? And the lowest point is at 0, 0, and it goes through 1, 1, 2, 2, 3, 3, and -1, 1, -2, 2, -3, 3, and so on. Right, so here's y equals the absolute value of x. Right, that's that graph. Alright, then I'm going to perform some transformations. Now, again, I pointed this out in a previous video on graphing using transformations or performing sequences of transformations, so hopefully you've seen those. I prefer going through the vertical transformations first, then the horizontal transformations. And when I do the vertical transformations, I prefer doing the multiplication first, stretches, compressions, or reflections, and then the shifts, right? Then the adding or subtracting, moving it up or down. And when performing horizontal transformations, I do it the other way. I do the shifts first, moving it left or right, and then replacing x with a number times x to cause a horizontal compression or stretch, or even a reflection if it's a negative number. So looking back at the graph, the lowest point here of this V shape is 3, -2. So there's definitely going to be some shifts eventually, right? Because the lowest point of our toolkit function is 0, 0. So we're going to be moving right 3 and down 2 eventually. Right, but first I want to do a vertical stretch or compression. Right. So notice that lowest point right? 3, negative 2. If I go right 1 unit, I have to go up 2 units to get back on the graph. Same thing if I go left 1 unit, I have to go up 2 units to get back on the graph. Well, if you look at the original, if you go from the lowest point here, which is sometimes referred to as the vertex, if I go right 1 unit, I only have to go up 1 unit. Right? This is only a distance of 1 unit here to get back on the graph. But on the graph they're giving us, if you go from the bottom point right 1 unit, you have to go up 2 units. So 1, 2. Left 1 unit, up 2 units, 1, 2. So the point 1, 2 and negative 1, 2 will be on this new graph. All right, we're gonna actually cause a vertical stretch by a factor of 2. Right? Instead of going, right 1 up 1 to get on the graph, I'm going right 1 up 2. Right? That distance is doubled. So we would next do a vertical stretch by a factor of 2, and I'm going to be assuming here that you know how to perform your function transformations by now. Alright, I've done them in previous videos, so I'm not going to explain all of the transformations again. Right? And to do this, you just take your previous rule and multiply it on the outside, by 2. So I'm going to graph now y equals 2 times the absolute value of x, and I'll do this in this green color, and that's this. Alright, so there's the next graph. So this was y equals, absolute value of x. Here's y equals 2 times the absolute value of x. Right? A vertical stretch by a factor of 2. Alright. Then, again, looking back at the graph we want, instead of having the lowest point be at 0, 0, it's at 3, negative 2. So I eventually have to move this down 2. Right? So let me do that next. So shift down 2 units. And that's simple enough, right? You take your previous rule and just subtract 2 outside, right? Take the previous rule, leave it the way it is, and then just subtract 2. That'll move the graph down 2 units. So instead of 0, 0, you'll be at 0, negative 2. And then this 1, 2 here moves down to 1, 0. And then negative 1, 2 moves down 2 to negative 1, 0. And we basically, we get the same graph as that green graph. I have 2 times the absolute value of x. Just move down 2 units. And bear with me here. This is gonna get pretty cluttered. I'm eventually gonna go to the Desmos website and make better looking graphs. Right, so now we're here on this pink graph, and then the final transformation I would need to, now I'm done with the verticals, right? I'm done with the verticals. I did the vertical stretch by a factor of 2, did the vertical shift, down 2 units. Now let's do the the only horizontal transformation I'm noticing is that I would have to take this point here at 0, negative 2 and move it to the right 3 units, right? Because again, back on this graph, the lowest point is at 3, negative 2. So now all I'm going to do is shift right 3 units. Right, so I'll do this here. Right shift 3 units. And hopefully you recall how to do that, right? That means you just replace all the x's in the previous rule with x minus 3, right? The quantity x minus 3. So now we're looking at y equals, take the previous rule, 2 times the absolute value of, and then instead of x, that is now x minus 3, and then you still have the minus 2, right? Everything else stays the same. The only thing I'm changing is the x to x minus 3. And here it is. This is going to be the equation for our graph. Now let me actually draw it. All right, so if I move all the points on the pink graph to the right 3 units, we'll have 0, -2 moves to 3, -2. 1, 0 moves to 4, 0. -1 right through 3 units moves to 2, 0. Right? -1, 0 moves to 2, 0. And it's that same, pink graph moved to the right 3 units. And this orangish graph I'm drawing here is the final graph, right? Y equals 2 times the absolute value of x minus 3 minus 2. And there we go. Right, this is a good equation for that graph. And let's see, right, this orange graph here that has 3, -2 on it as the lowest point. So does this graph. Right, see 3, -2. This has 4, 0 and 2, 0 as its x-intercepts. So does my orange graph. So this is a perfectly valid equation for the graph they gave us. Right, so that's why I've circled it twice. And then just to look at some better looking pictures of this, right, let's actually, I'm going to go to that Desmos website, right, desmos.com. It's a free online graphing calculator. And I'll do the same thing I just did by hand. We'll start off with that toolkit function, y equals the absolute value of x. You can just type ABS for absolute value. Then we did a vertical stretch by a factor of 2, right? So I just multiplied by 2. There's that blue graph, right? All the points on the blue graph are twice the distance from the x-axis as the points on the red graph. All right, and now, so now we're on the blue graph, and then we shifted this down 2, right? So I took the previous rule and then just subtracted 2, right? So now the green graph is all the points on the blue graph, right? Shifted down 2 units. And then finally we shifted this green graph to the right 3 units by replacing the x in the previous rule with x minus 3, right? That shifts it to the right 3 units and get the purple graph there. And this is the graph they asked us for, right? It has the point 3, -2 at the bottom. It has 4, 0 as an x-intercept, 2, 0 as an x-intercept, and a y-intercept of 0, 4, right, which you look back here. Now that, the arrow's continuing on, but you can see that this would cross the y-axis at 0, 4. So it is the same exact function. Great. All right, so next example. Right, so yeah, that again, I'm assuming that you know your transformations now well enough by now to be able to do this. All right. Okay, next example I want to do is the try it problem number 2 from the text. All right, so let's go back to the text, which I'm at here, and then scroll down a bit. Here's try it number 2. And this is just like in a previous video on creating, performing a sequence of transformations. We're asked to write the equation for the absolute value function that is horizontally shifted left 2 units, is vertically flipped, right? So that means reflected across the x-axis, right? And then vertically shifted up 3 units. So I'm going to start off. Right, so we're starting again with the basic toolkit function, right? The absolute value function. Then they asked us to perform the following transformations in this order. The first one they asked us to do was horizontally shift, right? Do a horizontal shift left 2 units. And again, I'm hoping you recall how to do this. To do a shift left 2 units, you're replacing all the x's with the quantity x plus 2. So now instead of y equals the absolute value of x, it's going to be the absolute value of x plus 2. The graph of this function would be the graph of that one, shifted left 2 units. Right, then we're asked to vertically flip this function. Right? Vertically flip. In other words, reflect across the x-axis. Right, do a reflection. reflection across the x-axis, right? A horizontal flip would be across the y-axis. Alright, and again, I'm hoping you remember how to do this. You just multiply the rule by -1. It's that simple. Multiply the previous rule by -1. Alright, so you don't replace x with anything. You just take the previous rule, the way it looks, absolute value of x plus 2, and then just simply multiply it by -1. Throw a negative sign in front of it. So then this graph, the graph of this function, will be the graph of the previous function flipped over the x-axis. And then the final transformation they ask us to do is vertically shift up 3 units. Remember the vertical shifts, vertically flipping, vertically shifting. The vertical transformations, you just keep the rule the way it is and then do something outside of it. This would just be simply adding 3, right, to move the function up 3. So we end up with y equals, take the previous rule, -1 times the absolute value of x plus 2, and then we're just adding 3 to this rule, and there we go. Here's an equation for the absolute value function they just described. Alright, and once again, I'm going to go to the Desmos site and show you that these are the actual transformations that are occurring. So once again, we're starting with the absolute value function, right? Y equals absolute value of x. Right? Then they told us to shift it left 2 units. So y equals the absolute value of, and then x is replaced with x plus 2. And you see the black graph that just showed up is the original graph moved left 2 units. I hope you can see that. Alright, so now we're on this graph. Then we were asked to vertically flip it. Alright, flip it across the x-axis. And that's just taking the previous rule and multiplying it by -1. So now I have -1 times the absolute value of x plus 2, and do you see that? The black graph and the red graph. This graph that just showed up is the previous graph flipped across the x-axis, vertically flipped. And then we were asked to move this up 3, right? So just take the previous rule, negative absolute value of x plus 2, and then simply add 3. Right? And you see the new graph that just showed up is the previous one, where all the points are shoved up 3 units, shifted up. And there we go. There's our final function, the final graph, and all the transformations they described did occur, right? Hopefully you saw all those. Great. Alright. So now the next examples, and I think this is the case for the rest of the examples I have in the video. I'm just flipping through here to make sure. Yeah. So for the rest of the examples, the last 11 examples I have for you, it's a bunch, I have the following instructions. First, I'm going to find the x and y intercepts of the graph, if any. Alright, I should say if they exist, because we are going to see that some of these absolute value functions might not hit the x-axis. Right, you could have, here's a tiny picture. Say there's the x and y axis. You could have an absolute value function that does this, where the lowest point is above the x-axis, and it goes up, and the graph doesn't actually touch. So that's why I'm saying, if any, because there may not be x-intercepts. Now there will be a y-intercept for all these absolute value functions, I promise you. Right, and then graph the function. Alright, now I'm going to graph this first function in a couple of ways, and then go through like the quicker way for the rest of them. One way to graph is using transformations, right? Perform one transformation at a time. And then I'll show you a second way to graph absolute value functions, these absolute values of linear functions. And it's a way that I prefer. It's just a lot faster. And I'll do that for the rest of the examples. Okay, so first let's find x-intercepts, if any. Let's put x-ints. Now remember, x-intercepts are points on the x-axis, meaning that the y value is 0. So let y equal 0, or, in this case, f of x, replace that with 0. And then we solve for x. So we're solving this equation, right? We have 0 equals, and then we have negative 3 times the absolute value of x minus 2 minus 1, right? And we're solving this for x. So hopefully you remember this, right? This has been brought up in a previous video. I don't know how long it's been, but to solve an absolute value equation, you isolate the absolute value. So this absolute value of x minus 2, going to get that alone. So we would add 1 divided by negative 3. So we'd have the absolute value of x minus 2 equals, 1 divided by negative 3, that's negative 1/3. This can't happen. Because remember, the absolute value of something, right? The absolute value of any number, any real number, is non-negative. Right? The absolute value of 5 is 5. The absolute value of negative 5 is also 5. The absolute value of 0 is 0, and so on. You're never going to get the absolute value of a real number being equal to a negative number, right? This is a problem. Right, so a non-negative number can't be equal to a negative number. This can't happen. And if the equation you're trying to solve has no solutions, that just means the equation has no x-intercepts. So it'll be like one of these, where the graph has, is not crossing the x-axis at all. So this graph is going to have no x-intercepts. Now the y-intercept will exist, I promise, for all these. Right, so for the y-intercept, right, you just replace x with 0. Right, you'll be on the y-axis somewhere. So that's where the x coordinates are 0. So we have, f of 0, which is the y coordinate when x is 0. Or you could just put y equals negative 3 times the absolute value of 0 minus 2, and then minus 1. Alright, so this is negative 3 times the absolute value of negative 2, and then minus 2, and the absolute value of negative 2 is positive 2. So this is negative 3 times positive 2 minus 2. Then you do multiplication first, right? This is negative 6 minus 2. This is negative 8. So from all this here, the y-intercept is the point 0 for x, negative 8 for y. All right, and I'll plot that when we go to graph the function. Right. But now let me talk about graphing the function. Right. So keep these in mind, right? It's not going to cross the x-axis, and it's going to cross the y-axis at the point 0, negative 8. All right. Now, negative 7. My apologies. You're probably yelling at me right now. I put minus 2 here, didn't I? It's minus 1. Yikes. Glad I caught that. So that'd be negative 6 minus 1, which would be negative 7. My apologies. Again, I hope you weren't getting too frustrated with me just watching me make this mistake. Okay. So yeah, actually copying the problem down correctly, we see that, again, the graph's not going to cross the x-axis. It's going to cross the y-axis at 0, negative 7. Again, my apologies. All right, so now for graphing. As I mentioned earlier, I'm going to show you two different ways we're going to do this. And one of them is much faster in my opinion, and I'm going to do the faster way for the rest of the examples. You can do the longer way if you want, but method 1 is using transformations, which would be nice for you to practice, right? Get used to these transformations again if you haven't been used to them in previous sections after watching my previous videos on performing sequences of transformations. So f of x here is negative 3 times the absolute value of x minus 2 and then minus 1. Right? So it's an absolute value of a linear function, right? So that's what I'm going to start with. Y equals the absolute value of x, which looks like this, as you know, and we saw this already, 0 0 1 1 and negative 1 1, right? And it's this graph here, right? And you know what, just to reduce a little clutter, I'm going to call this number 1. All right, this is graph 1. So I put the number 1 there. Right? And what I'm going to do is I'm going to perform transformations until we get this rule. Instead of just being the absolute value of x, I want to take one step at a time and make it look like this rule. Negative 3 times the absolute value of x minus 2 and then minus 1. Okay. So as I mentioned before, I prefer doing the vertical transformations first, right? All the outside stuff, the stuff outside the absolute value, and then the horizontal transformations, right, where I replace x with something, right? Replace x with something plus x, x plus something, x minus something, or x times something. All right, so the first thing I'm noticing is that this is multiplied by a negative number, so that's going to be our reflection. So we're going to first reflect across the x-axis, which means multiply this by negative 1. Y equals negative 1 times x, right? And this will be graph number 2. All right, so 0 0 will stay 0 0. 1 1 will reflect to 1 negative 1. Negative 1 1 will reflect to negative 1 negative 1. Right? And we have this graph now. So again, my picture is going to get very, very cluttered soon. There we go. All right, there's graph number 2. Right, it's the same graph reflected across the x-axis. But also, not only as I multiply by negative 1 on the outside, but it's multiplied by negative 3, so then I'm going to multiply this by 3 to make it negative 3 times the absolute value of x. And if you multiply a rule by 3, that's going to cause a vertical stretch by a factor of 3. So now we have y equals negative 3 times the absolute value of x, right? And this will be graph number 3. So it's just going to take the points on my second graph and multiply all the y coordinates by 3. All right, so instead of 1, negative 1, that'll be at 1, 3, negative 3. 0, 0 will still be at 0, 0. Right? 0 times 3 is still 0. And then negative 1 will be at negative 1, negative 3, right? And you get this vertical stretch by a factor of 3. Right, so now I'm making a pink graph. Right, so this is graph 3. All right, and then the final vertical transformation is I got this minus 1 outside the absolute value here. So I take my previous rule and just subtract 1 from it. That'll shift it down 1. Right? So let's say shift down 1. So we have y equals negative 3 times the absolute value of x and then minus 1. And this will be graph number 4. So again, I'm going from graph 3, the pink graph, down 1. So 0, 0 will move to 0, negative 1. 1, -3 will move to 1, -4. -1, -3 will move to -1, -4, and I get this graph in like an orangish color here. If you can't make out the colors, don't worry about them. I'm writing numbers next to them. That's graph number 4. And then finally, right, the only other, now I'm done with the vertical transformations, right, the stuff done outside the absolute value. Now let's go inside. The only thing I need to do now is replace x with x minus 2, right, to get the absolute value of x minus 2 instead of the absolute value of x. And hopefully you recall that if you do that, if I replace x with x minus 2, that's going to cause a shift, a horizontal shift to the right 2 units. So we have y equals, f of x. Right? We have our f of x now, -3 times the absolute value of x minus 2, and then minus 1. This is what we started with. Well, this is what we wanted to end up with, right? F of x. And this will be graph 5. All right, this will be graph number 5. I'll make this brown or something. All right. So now I'm taking graph number 4, moving all the points to the right 2. So 0, -1 goes to the right 2 to 2, -1. Then 1, -4, you're moving that to the right 2 to 3, -4. And then -1, -4 moves to the right 2 to 1, -4. And we get this graph here. I know this is crazy cluttered, so I'm definitely going to the Desmos site. There's graph 5. There's the graph of our function. Alright, so I'm going to go to the Desmos site and do the same thing, but make it less cluttered. But our final graph is this 5th graph here, this brown V-shaped graph opening down. And notice, right, it doesn't hit the x-axis, and it should hit the y-axis at 0, -7, right? We said that on the previous page, right? This should be -7 here where it hits the y-axis if I were to continue it. All right, but let's see that in the Desmos site, right? We'll have a much better looking drawing on this graphing calculator. All right, so once again, we started with the basic absolute value function, and then I multiplied it by -1, right? We reflected it across the x-axis, right? So now I got the green graph, right? This was graph number 2 on my paper. And then I multiplied this by 3, right? Y equals -3 times the absolute value of x. And you see that was the 3rd graph I drew, and this was a vertical stretch by a factor of 3. Right, all the points on the purple graph are 3 times the distance from the x-axis as the points on the green graph. Right, and then subtracted 1 from this, moved it down 1, -3 times the absolute value of x, and then -1. And you see the black graph is just a purple graph, moved down 1. Now we're here. This was graph number 4. And then finally, replacing x with x minus 2 shifts this to the right 2 units. Y equals -3 times the absolute value of x minus 2, and then -1. And you get that red graph, and this is the final graph. All right, and look at this. When I click on this thing, the highest point is 2, -1, which is what I had on my picture for graph 5. And you see again, there's no x-intercepts, not hitting the x-axis at all, which we said. And look at the y-intercept, 0, -7, which is what we said as well. So this is perfect. All right. All right, so that is one way to graph these. All right. Take a look at, perform the transformations. Start with your basic absolute value function, and then perform, one transformation at a time until you get the equation that you want, right? And then that should be your final graph. Now, the second method I'm going to show you is specifically for absolute value of linear functions. Right? So you see I have the absolute value of a linear here, x to the 1st power linear, right? So method 2 is, again, just for these. Now, I've mentioned this out loud. This point that's at the highest point or the lowest point, you know, of these V-shaped graphs is called the vertex. So the first step is finding this vertex. All right, this is the highest or lowest point of this V shape. Now the x-coordinate is simple. All right, the x-coordinate of the vertex is simply the value of x that gives you 0 inside the absolute value symbol. The value of x that makes the expression inside the absolute values equal to 0. So for example here, I have the absolute value of x minus 2. So where is x minus 2 equal to 0? That happens when x equals 2. All right, so this is going to be the x-coordinate of this vertex point, right? This point that's at the highest or lowest point of the V shape. And then the y-coordinate is just plug in the x-coordinate. You know, the y value after plugging in the x-coordinate. All right, so what's f of 2? All right, just replace x with 2 here. We have negative 3 times the absolute value of 2 minus 2. And again, it should make the absolute value 0. All right, that's the whole point of this first part. And then minus 1. This is going to be negative 1. All right, 0 minus 1. So this vertex here is 2, negative 1, which you saw. See this fifth graph again, the final graph from my transformations? 2, negative 1. 2, negative 1 is that vertex. And then just find a point on either side. Because you know these are going to be V-shaped. All right, and again, this is for absolute value of a linear only. Please know this. This method I'm using is only for these kinds of functions. Very, very specific. Find a point on either side. So x equals 2 is where the middle is, right? That's where the vertex is. So let's pick a value to the right, value to the left. So say x equals 1. F of 1 would be negative 3 times, the absolute value of 1 minus 2, and then minus 1. Now this would be, 1 minus 2 is negative 1. The absolute value is 1. So this is negative 3 minus 1. That's negative 4. So 1, negative 4. And then you can use symmetry. Actually, these are all symmetrical about the vertex. Right. So we got 2, negative 1 is a point, and then 1, negative 4 is a point. And then using symmetry, right, because I know this vertex point is in the middle. This 1, negative 4 is 1 unit to the left, so there should be a point 1 unit to the right as well at 3, negative 4. And then we graph it. Right. And there we go. Now, you could also use the, we found the y-intercept earlier was 0, negative 7. I could have used that point. But this graph I just drew here is exactly the same as the graph I drew here. It's got 2, negative 1, it's got 1, negative 4, it's got 3, negative 4, right? It's got 0, negative 7, 4, negative 7, right? It would have all those points. And that's it. Okay, now the underlying reason this all works is because of the transformations, all right? So you should still, I would say maybe every other problem, practice doing the transformations, right? You should still know how these transformations work. And again, like I said, the underlying reason why this method works is because of the transformations. Right? So you should still know how to perform the transformations, still know how to use them, how to work them, how to graph them. But yeah, let me just tell you that from here on out, I'm going to be using method 2. Right. Okay. So again, next example, and all the rest of the examples, I'm doing the same thing as I did for example 3. So first we're finding the intercepts. Right, so here we have f of x equals -5 times the absolute value of x plus 2, then plus 15 after. So again, you can do so first we'll do the intercepts. Right? X-intercepts, you replace f of x with 0 or y with 0. So that leaves me with this equation: 0 equals -5 times the absolute value of x plus 2, and then plus 15. Right? And then remember, we isolate the absolute value to solve this equation. So I would subtract 15, divide by -5. We'd have the absolute value of x plus 2 alone on one side and 3 on the other, positive 3. Now this can happen. Absolute values can be positive. Now all you have to do now is think, what numbers have an absolute value of 3? Well, that's 3 and -3. So this x plus 2 can be equal to 3, or this x plus 2 could be equal to -3, and this would be a true statement, right? The absolute value of 3 is 3, the absolute value of -3 is also 3, and then you solve each of these. So here x equals 1, here x equals -5, right? So the x-intercepts are 1, 0, and -5, 0. All right, and I'll plot those. Again, very rough sketch here, and I'll go to the Desmos site. We'll look at a much cleaner picture. But here's 1, 0 is on this graph, and also -5, 0 is on this graph, right? And you can double check that. Replace x with 1, you get -15 plus 15, that's 0. Replace x with -5, you'd get again -15 plus 15, that's 0. So 1, 0, 5, 0. The graph is crossing the x-axis this time. Alright, then the y-intercept is a lot easier, right? Just replace x with 0, and you find f of 0, right? Well, that'd be -10, right? 0 plus 2 is 2. The absolute value of 2 is 2. -5 times 2 is -10. Plus 15 is 5. So 0, 5. And I'm going to do this. I'm going to do this actually. We're just going to have each notch in the y-axis be 5 units. You'll see why in a second. So 0, 5. All right, 0, 5 on the y-axis. Great. And now let's graph. So I have a bunch of points. All I need now is really to find the vertex. Right? Find the vertex, that highest point or lowest point. The expression inside the absolute value is x plus 2. So when is x plus 2 equal to 0? That's when x equals -2. And then we plug that in, right? What's f of -2? That'll be 15, I promise you, right? Because again, this is going to be 0 when x is -2. And then you just got 15. So the vertex is at the point -2, 15. So -1, -2, right? -2, that's why I did the little 5 notches here. There's the vertex, right? -2, 15. And I have enough points now to graph this thing. There's a point on the left, a point on the right, So from the vertex through the points on the left, and from the vertex through the points on the right. And there you go. Right, there's the graph of this function f that was given to us. All right, wonderful. So yeah, that's a lot. Again, I like doing this for these absolute value of linear functions. You don't have to. Again, you could do transformations, right? Start with the absolute value of x, then I'd be doing reflection across the x-axis, vertical stretch by a factor of 5, shifting up 15, and then shifting left 2. And again, I hope you see all that. And I'll do that. I'll describe the transformations that would occur. But I'm going to be doing the graphs this way from here on out. All right, now let's go test. Let's go verify our solution. Let's go back to the Desmos site here, and I'm going to enter the graph of the function they gave us. Right, that was f of x equals -5 times the absolute value of x plus 2, and then plus 15. And if I look at this, let me zoom this out. Click on it. See, the high point is at -215. That's that vertex. Here's 0, 5, right? The y-intercept that we said. Here's 1, 0, -5, 0. Right? It's the exact same x-intercepts, y-intercept, and vertex that I put out on my piece of paper. So, good graph. Excellent. All right, next example. Same thing, right? So first I'll find the intercepts. All right, so x-intercepts. When is f of x equal to 0? All right, so when is 0 equal to the absolute value of -2x plus 1, and then minus 13. So remember, you isolate the absolute value. So the absolute value of -2x plus 1. When is this equal to? I would be adding 13. Okay. And this is going to happen when this can happen. Absolute values can be can be positive numbers, right? Positive 13. The only numbers that have an absolute value of 13 are 13 and -13. So this will happen when -2x plus 1 is 13, or when -2x plus 1 is -13. And this happens when x is -7. Nope, -6. Sorry, 12 divided by -2 would be -6. So -6, 0 is an x-intercept. And here, subtract 1, you get -14 divided by -2 is +7. All right, so the x-intercepts are at -6 and +7. And I'll plot this. Again, I'm going to make a pretty rough sketch here. So 1, 2, 3, 4, 5, 6, 7. There's one x-intercept that points on the graph. And then 1, 2, 3, 4, 5, 6. -6 is another x-intercept. Great. Alright, now y-intercept, very simple. If x were 0, this would be 0 plus 1 is 1, absolute value of 1 is 1, 1 minus 13 is -12, right? F of 0 is -12, so 0, -12 would be the y-intercept. Right, there's -12 on the y-axis, and there's the y-intercept there. Okay. All right, and then finally the vertex should be all I need to be able to graph this thing. Now, take the expression inside the absolute value symbols, -2x plus 1, and say, hey, where's that equal to 0? Well, that's equal to 0 when x is a half. So here's 1. So here's 1/2. Right, 1/2. And then f of a half would be -13. Right, so the vertex is at 1/2, -13. 1/2, and then -13 would be down here. So a little bit to the right of the y-axis right there. There's the vertex. There's 1/2, -13. And then, I can draw it now. From the vertex through the points to the left, and then from the vertex through these points to the right, and there you go. There's the graph of the function they gave us. Right, very, very rough sketch. Now let's verify this. So I'm going to go to the Desmos site and see that we do get this same picture. All right, And then I'll describe the transformations that would occur if you were graphing with transformations. I'll just do that out loud. All right, so we have f of x equals the absolute value of negative 2x plus 1, then minus 13. All right, and let's see. See the x 7, 0, negative 6, 0. All right, the same x-intercepts that we said. The y-intercept is highlighted, right? It's 0, negative 12, like I had in my graph. And look at the vertex, 0.5, comma, negative 13. That's 1/2, negative 13. That's exactly the vertex I pointed out earlier on my paper. So this is a perfect graph. All right, my drawing earlier is the same as this drawing, just not as clean looking. And to describe if you were doing this with transformations, you'd start with the absolute value of x. Then I'd shift it, down 13, and then replace x with x plus 1 to move it left 1. Then replace x with negative x to reflect it across the y-axis, and then replace x with 2x to cause a horizontal compression by a factor of 1/2. And again, I'm assuming you know all your transformations. I'm not going to go into all that again. But if you were doing transformations, that's the order that I would prefer to do it in. Right. And then you create this graph finally at the end. Okay. All right, example 6. Again, the x-intercepts, let's do those. Right, replace y with 0. So we're solving this equation. And this only happens when x equals 1. So the only x-intercept is 1, 0. Right. The absolute value of 0 is 0. So when x minus 1 is 0, that'll be true. So only when x equals 1. So there's a 1, 0. There's the x-intercept. Y-intercept, put in 0 for x. Y equals the absolute value of 0 minus 1. That's just y equals 1. Right? So 0, 1. Y-intercept. And the vertex would be 1, 0 again. Right? Because x minus 1 equals 0 when x is 1. We already have the so this is the vertex as well. And I can use some symmetry. Remember, the vertex is in the middle. It's going to be symmetrical about the line x equals 1. And you go 1 unit left, 1 unit up, do the same thing on the other side. 1 unit right, 1 unit up. Now obviously you can just plug in 2. Right? 2, 1 is also on it. Right? 2, 1 is on this graph. Plug in 2 for x, you get 1 for y, and there you go. That's enough to graph it. You have a vertex, point on the left, point on the right. You go from the vertex, through the points on the left, and then draw a ray through the points on the right, and there's your graph. Yeah, that's it. And it can really be that quick. And it would be easy with transformations too, right? If you start with the absolute value of x, all you would need to do is replace x with x minus 1 and just shift it to the right 1 unit. Right, this is just the graph of the absolute value of x shifted to the right 1 unit. Right. And again, just let's verify this. Right. So let's clear that. And it's just y equals the absolute value of x minus 1. And see, there's 1, 0, 0, 1. And here's 2, 1. There you go. Right, and it's this V shape opening up like I have on my picture. Alright, easy enough. Next example. Alright, this one's even easier. Just take the absolute value of x and shift it up 1. So, this is going to have 0, 1. And instead of 1, 1, it'll be 1, 2. And instead of negative 1, 1, it'll be negative 1, 2. And the vertex is at 0, 1. Like, I don't know. I'm not going to draw all that. I'm not going to write all that stuff. There we go. There's our graph. Easy enough, right? Again, it's just the original absolute value function moved up 1 unit. Very simple. All right, I'm not even gonna go to Desmos for that one. That one's simple. All right, here's another pretty simple one. y equals, negative absolute value of x. This is just the absolute value of x reflected across the x-axis. Right, you'd have 0, 0, and then instead of 1, 1, you'd have 1, negative 1. Instead of negative 1, 1, you'd have negative 1, negative 1, and there you go. Vertex is 0, 0. Graph opens down. There you go. And again, this is a very, very simple one. It's just the absolute value of x reflected across the x-axis, which I have here. All right, again, very simple one. I'm not going to Desmos for that. All right, the next one's a little more involved. There are more transformations if you were doing transformations. So this one, x-intercepts, put in 0 for y, and we'll solve this for x. Well, if you isolate the absolute value of x minus 3 would be equal to 2. Well, actually, negative 2, and that can't happen. Alright, because I would add 2 divided by negative 1. You'd have negative 2 on the other side. And the absolute value of a real number, can't be negative. Alright, so no x-intercepts. And then the y-intercept, right, just replace x with 0. If x were 0, this would be 3, but, then negative 3, because you got the minus out here. Negative 3 minus 2 is negative 5. So I have 0, negative 5 as the y-intercept. And the vertex, I'm hoping you see, would be at the point 3, negative 2. Because where is x minus 3 equal to 0, right? That's at x equals 3. So that's the x coordinate of the vertex, right? Just take the expression inside the absolute value symbol, set it equal to 0, and solve. And if I plug that in, I get 0 here and then minus 2, right, for the output. So 3, negative 2 is the vertex. And then I can use symmetry. From the vertex, I go, left 3, down 3 to get to this y-intercept. So I go on the other side, the same thing. Right 3, down 3. Plug in 6. Right 3, down 3. You should have 6, negative 5 as well. And check it out. If I replace x with 6, 6 minus 3 is 3. Absolute value of 3 is 3. Then you have negative 3 minus 2 is negative 5, right? So 6, negative 5 would also be on it. And then I draw from the vertex a ray through the points on the left, and then through the points on the right, and there we go. There's the graph of our absolute value function. Now, if I were doing transformations, I'd start with the absolute value of x. I'd reflect it across the x-axis, then move it down 2, and then move it right 3. And let's do Desmos. Right? In fact, let me actually write out that sequence of transformations, right? So I start off with the absolute value of x, and then you had the negative 1 on the outside, so that reflects it across the x-axis, right, giving me this graph. And then you have the minus 2 after, which will move it down 2. Alright, now it's moved down 2. And then x is replaced with x minus 3. So y equals negative absolute value of x minus 3. Then minus 2, and then it's moved to the right 3 units. The black graph to the red graph there. And there we go. And you see there's 3, negative 2, as I said, would be the vertex. 0, negative 5, the y-intercept, as we said. Over here, here's 6, negative 5, as we said would be on the graph as well. All right, this is the graph that I drew by hand. Just a lot cleaner looking. Alright, and actually, you know what? I'll do this for the rest of the problems. We'll actually just go through the transformations that would be performed. Why not? Okay. Alright, next example. Alright, so here we're given this function. Let's look for the x-intercepts. So where is negative absolute value of x plus 3 plus 4, where is that equal to 0? So where is the absolute value of x plus 3 equal to 4? Well, that's going to be when x plus 3 equals 4, or when x plus 3 equals negative 4. So when x equals 1, or when x equals negative 7. Alright, so my x-intercepts are 1, 0, and negative 7, 0. And some rough sketches here. So 1, 0 and negative 7, 0. Again, very, very rough. Alright, then the y-intercept, again, very simple. Just plug in 0 for x. And if I do that, this will be 3, but then you have negative, so negative 3 plus 4 is 1. So 0, 1 will be the y-intercept. And then the vertex, again, should be easy to find. The x-coordinate would be negative 3, right? What makes x plus 3 equal 0? That would be negative 3. And if I plug in negative 3, this first term will be 0, and then plus 4. So negative 3, 4. There. And I have everything I need to be able to draw this, right? Negative 3, 4 for the vertex, and then I draw, through a ray through the points on the left, which is through that point negative 7, 0, and then through these points on the right. And there we go. All right, there's the graph of our absolute value function. Now again, if I were doing transformations, I'd start with the absolute value of x, reflect across the x-axis because this times negative 1 here, then move it up 4, plus 4 on the outside, and then replace x with x plus 3 to move it left 3. And let's do that. All right, but not by hand. All right, again, I'm just going to go back to Desmos. We'll start with the absolute value of x. I said let's multiply it by negative 1 to reflect across the x-axis. Alright, then we're on this graph. Then I add 4 to move it up 4. See, it moved up 4 now. And then replaced x with x plus 3. Sorry, we're on this graph. Then replaced x with x plus 3 to move it left 3. You see the graph of the green is moved left 3 to be this purple graph. And this has all the points that I drew by hand, right? The vertex is negative 3, 4, as I said. The y-intercept is 0, 1, and the x-intercepts are 1, 0, and negative 7, 0. Exactly like I wrote out on paper. Great. All right, next example. So again, I'll do the intercepts, right? X-intercepts. So where is this output going to be 0? 3 times x, absolute value of x minus 2 plus 3. Where is this going to be 0? In other words, where is the absolute value of x minus 2 going to be equal to negative 1? Never. This can't happen. Can't have absolute value equal to a negative number. So there are no x-intercepts, right? Now the y-intercept, again, very simple. Just plug in 0 for x. And this would become negative 2, but then the absolute value is 2. 3 times 2 is 6, plus 3 is 9. Right, so you got 0, 9 as the y-intercept. A very rough sketch here. There's a point on the graph, 0, 9. And the vertex would be easy enough again, right? Just the x-coordinate would be 2, right? What makes the expression in the absolute value equal 0. And if x were 2, the output would be 3. So 2, 3 for the vertex. And if 0, 9's on it, then 4, 9 would also be on it, right? Using symmetry. And you can test that out. Replace x with 4, you should get an output of 9. And then from the vertex, through the points on the right, vertex through the points on the left, and I get this, this V-shaped graph here. There's the absolute value function. And let's test this out. Now, if I were doing transformations, I'd start with absolute value of x. Then we got the times 3 for a vertical stretch by a factor of 3. Then there's the plus 3. You shift up 3 after that. And then replace x with x minus 2 to shift it right 2. Right, let's see those happening back in Desmos. Right, so again, we're starting with the absolute value function. Then I said let's put that times 3 in front of it. Right, this will cause a vertical stretch by a factor of 3. Hopefully you can see that. Then I added 3 to this, moving it up 3. Right, so take the previous rule and just add 3. That moves it up 3 units. And now we're taking this and replacing x with x minus 2, shifting it to the right 2 units. All right, and it shifts that graph right 2 units, and here we go. And look, see the vertex 2, 3, just like I said. The y-intercept 0, 9. And then look on the other side, there's 4, 9. There it was, right? Just like I had on my paper, and it's exactly the same graph I drew. Wonderful. Okay, great. Next example. So again, we'll just got a couple more of these. All right, so this time again, I'll start trying to find the intercepts, right? The x-intercepts. Where is the absolute value of 3x plus 9 plus 2? Where is that equal to 0? Well, this will happen when the absolute value of 3x plus 9 is equal to negative 2. Oh, that can't happen. Can't have an absolute value equal to a negative number. So there are no x-intercepts. Y-intercept is pretty simple. Right, just replace x with 0, and then this would be 9 here. 9 plus 2 is 11. So again, very, very rough sketch over here. Right, there's 0, 11, the y-intercept. Now the vertex, what value of x makes 3x plus 9 equal 0? That'd be negative 3. So negative 3 for the x, and if I plug in negative 3, this would be 0, and then plus 2. So negative 3, 2 is the vertex. And if 0, 11 is on this, using symmetry, we'd say negative 6, 11 would also be on this, right? And if you plugged in negative 6, you'd see the output would be 11, right? Because you'd have negative 18 plus 9 is negative 9. The absolute value of negative 9 is positive 9. 9 plus 2 is 11. And, there we go. From the vertex through the points on the right, from the vertex through the points on the left, and here's our graph. Right. Now, if I were performing transformations, I'd start with the absolute value of x, then move it up 2, right, with this plus 2. Then I would replace x with x plus 9 to move it left 9, and then I would replace x with 3x to cause a horizontal compression by a factor of 1/3. Right? Again, I'm hoping you remember all your transformations from previous videos, but let's see those happening. Let's see those happening. So again, starting with the basic absolute value of x, then I would just add 2 to this, right? Y equals absolute value of x plus 2. Moves it up 2. Now we're on this graph. Then I would replace x with x plus 9, right? Y equals the absolute value of x plus 9 and plus 2, right? And that shifts that graph to the left 9 units. Right, so now we're on this graph. And then I would just replace x with 3x. And that would cause a horizontal compression by a factor of 1/3. All the points on the purple graph here, their x-coordinates would be multiplied by 1/3. You're going to be closer to the y-axis, right? A horizontal compression. So we have y equals the absolute value of, and then x is replaced with 3x, and everything else is the same. You got the plus 9, plus 2, and then there you go, that black graph. And this graph is the graph we had, right? You see the vertex negative 3, 2, just like I said. Y-intercept 0, 11, just like we had, and then over here is negative 6, 11, just like I had. Right, there you go. And it's the exact same graph I drew on paper. All right, but performing one transformation at a time. Right. Okay, and then I got one final example. So again, let's start off by saying, what are the x-intercepts? So where is, negative absolute value of x plus 4 minus 3, where is this equal to 0? Well, this will happen when absolute value of x plus 4 equals negative 3, and oh, that can't happen. Damn. Right. Darn, sorry. Apologies for my language there. But yeah, this can't happen. Right, you add 3 divided by negative 1. Right, this can't happen. So no x-intercepts again. The y-intercept, easy enough, right? Just replace x with 0. This would be 4. Absolute value of 4 is 4. But then you have a minus here, so negative 4 minus 3, this would be 0, negative 7. And again, I'll put a little rough sketch over here. Right, there's -7 on the y-axis. There's a point on the graph. Vertex, again, pretty easy here. The x coordinate would be -4, right, where x plus 4 equals 0. And then pop that in, 0 minus 3, -3. So -4 for the x, -3 for the y. There's the vertex. And from the vertex, if the point 0, -7 is on this, then the point -8, -7 would also be on it, right? Just using some symmetry. Or you can plug in other numbers if you want. Just plug in -3, plug in -5, whatever. But I'm just using symmetry to make it a little easier on myself. And then from the vertex, through the points on the left, through the points on the right, there's the graph of our absolute value function. Now, if I were doing transformations, I'd start with the absolute value of x, then the times -1 would reflect it across the x-axis, the -3 would move it down 3 then, and then replacing x with x plus 4 would move it left 4. And let's see those happening. Right? So again, starting with the absolute value of x, I'm going to do the vertical reflection, right? Multiply by -1, reflects across the x-axis. Then the -3 moves it down 3. So keep the rule the way it is, and then -3, right, moves that down 3. And then replacing x with x plus 4 moves it left 4, and we get our final graph, right? Right, and you see that blue graph move left 4 for the green graph. And there's our final graph, and you see the vertex, -4, -3, like I stated. The y-intercept at 0, -7, like I had. And then over here, -8, -7, right, like I had on my picture. And it's the same graph I drew by hand, same exact stuff. All right, so as I've been saying, these absolute value of a linear expression functions, you can graph them in two different ways, right? You can do that first way I showed you with all the transformations, right? Doing one transformation at a time until you get to the final result. You just have to really know how to perform your transformations. And when I do this when I multiply a rule by -1, that reflects it across the x-axis. When I replace x with x plus 4, that moves it left 4. You have to remember what happens, when you perform certain transformations in that method. Or, you find your intercepts, you find that vertex, the x value is just whatever makes the expression inside the absolute value equal 0. Plug it in, you get the y value. And then make sure you get a point on the right of it, a point on the left of it, and then you should be able to draw the graph pretty quickly there, which is what I've been doing. All right. So yeah, so that was a lot. A little over an hour here, almost an hour 15. But I'm doing the same thing every time, right? And I'm hoping that watching me, go through these 13 examples of, you looking at the graphs and graphing these absolute value of a linear expression functions. Hoping this helps you out when you're asked to, graph an absolute value function on your own. And thank you very much for watching.